There is a variety of microwave power sensors on the market to meet your needs. CW average power sensors, peak power sensors, pulse power sensors, and even selective power sensors. However, the most common type is the CW average power sensor. In this video, I will be using the following devices: the MA24330A, a 33 GHz CW average power sensor from Anritsu, this entry-level 3 GHz Rohde & Schwarz FSC3 spectrum analyzer, and the 18 GHz Keysight FieldFox N9917A network analyzer, spectrum analyzer. In general, power sensors are considered to be more accurate than spectrum analyzers. And also, microwave power sensors in general are much less expensive than spectrum analyzers. Let's now see what to expect when measuring the power produced by the same waveform with a power sensor and a spectrum analyzer. Let's start by measuring an 80 MHz 1 volt peak-to-peak square wave centered at 0 volts DC. As we know, an ideal square wave contains only odd harmonics. However, that's not the case here due to distortions we always have in real world. Notice there is a 10 dB attenuator at the output of the generator. Here is the result of the measurement. For the spectrum analyzer, I measured the power from the fundamental up to the 7th harmonic, converted all to milliwatts, and then converted the sum to dBm again. Bear in mind that the accuracy of this particular spectrum analyzer at this frequency range is typically plus minus 0.5 dBm, and for the power sensor is about plus minus 0.1 dBm. Now let's repeat the measurement with the 2.8 GHz minus 10 dBm sine wave with low harmonic content and check the results, starting with the power sensor. Minus 10.14 dBm. Now the spectrum analyzer. Minus 10.4 dBm. The cable loss was considered in this measurement. Everything I have done so far has been in preparation for building a setup to extend the frequency range of my 18 GHz spectrum analyzer to 30 GHz. The setup is based on the ZMDB44H, a 30 GHz mixer from Mini Circuits. The first thing to do is to characterize my microwave generator, measuring its power output with a reliable and accurate power sensor. In this case, the Anritsu MA24330A, a 33 GHz CW average device. This is the setup to do that. Notice that at the output connector of the generator, I will always have this 40 GHz 10 dB attenuator to assure that the output impedance will be close to 50 ohms. And this is the result for a 0 dBm output. Now I need to characterize the 40 GHz mixer from mini circuits. To do that, I'm going to use this setup over here, which is actually the same setup I will use to extend the range of my spectrum analyzer. These modules here are the local oscillator providing 15 GHz plus 15 dBm to the LO port of the mixer. Here are the results for a 0 dBm output. Notice that all additional losses as cables and adapters were considered, and this column here shows the final result, which is the mixer losses. This other spreadsheet is the final product of my measurements. This column shows the correction that must be added to the level measured by the spectrum analyzer to obtain the actual level. I have already used similar structures in previous videos, but the measurement accuracy is now much better. As an example of use, let's now measure the second harmonic level of the 14.5 GHz signal generated by this synthesizer sold by AliExpress, based on the LMX2820. Let's see the spectrum analyzer. So the fundamental is 14.5 GHz, the second harmonic will be 29 GHz minus 15 GHz of the local oscillator. We have 14 GHz here at the spectrum analyzer. The level is 43 minus 43.9 dBm. We can see here that for 29 GHz we must add 14.4 dBm. 43.9 dBm plus 14.4, so the real level is minus 29.5 dBm. This technique could certainly also be used to double the range of a low-cost 1.5 or 3 GHz spectrum analyzer like this one. If that's something you'd be interested in, please leave a comment below. That's all I had. Thanks for watching.